Example number 7, an improved estimate. So we're going to use theorem 4 with n is equal to 10 to estimate the sum of the series of 1 over n cubed as n is equal to 1 to infinity. Now in step 1, the inequalities in theorem 4 become the following. S subscript 10 plus the integral of 1 over x cubed dx goes from 11 to infinity because that is n plus 1 here. And over on the right side, we have s subscript 10 plus 10 to infinity of the function 1 over x cubed dx. Now, from example 6, we know that 1 over x cubed going from n to infinity was equal to 1 over 2n squared. So we can say s subscript 10 plus 1 over 2 times 11 squared is less than or equal to s, which would be less than or equal to s subscript 10 plus 1 over 2 times 10 squared. So s subscript 10 is approximately 1.197532. So if we add that to this fraction here, then we get 1.201664 as the lower bound. If we add this value to 1 over 2 times 10 squared, the upper bound is going to be 1.202532. And if we approximate s by the midpoint of this interval, then the error is at most half the length of the interval. So 1 over n cubed is approximately 1.2021 with an error that's less than 0.0005. Now if we compare example 7 with example 6, we see that the improved estimate in 4 can be much better than the estimate s, which is approximately s subscript n. To make the error smaller than 0.0005, we had to use 32 terms in example 6, but only 10 terms in example 7. If we have used the comparison test to show that a series a subscript n converges by comparison with a series b subscript n, then we may be able to estimate the sum a subscript n by comparing remainders, as the following example is going to show.